geometry to actually express them in terms of the summation over different other local primary fields in a series. And in fact, we can fix the form precisely, including the field and also its descendant up to an overall coefficient. So since the 1970s, when conformal field theory was first studied, it was proposed by Ferrara and Mack and Patel that if we can actually summing over all this contribution, like including all the descendants for given primary field, we can try to call this thing a bilocal operator, and this was given the name of an OP block. And this I think is a fancy way of actually kind of rewriting the basically operator product expansion in conformal field theory. And the topic of today's talk, and also Tsuzuma's book, is about trying to find the holographic dual of this so-called OP block. So let's begin with the CFT, and I'm going to focus mostly on the Euclidean, since that's the easier part, and Tsuzuma is going to talk about all the glory detail, the Lorentzian case, and I think that's new. So, okay, so in order to actually find out the explicit form of this OP, we can consider what's known as the shadow projector. So this way, this basically is something like a rat and cat in the quantum field theory, and we are really treating this as something kind of eigenbasis. So here we are looking at the general primary field, and they are labeled by the scaling dimension and the spin. So the easy here is so we are working the embedding, the so-called embedding space for the Euclidean d dimension. This is going to be m1, d plus 1. So here everything will be expressed in the embedding space. And so dz here is the embedding space total operator. And this shadow projector basically involves the so-called shadow operator, which is the nonlinear, this is the integral transform involving basically taking a local operator, O delta, with J here, and basically use the integrated kernel, which is going to be a two-point function of this operator, the complementary dimension of D minus delta, and integrate it over the entire spaces in our case. So when we take this shadow projector and use the property of the two-point function orthogonality, then we can express this, to figure out a particular OP block and express this as an integral of the original operator O delta J, and also a three-point function. So the explicit function, so here the three-point function we are looking at the scalar tensor one, and that's the explicit form. The C0 here, this is the anti-symmetric combination, and this is basically unique in this case. So now if we consider, let's focus on basically, so P0 is the one corresponding to the one carrying the spin. So if we focus on the one which carry the P0 space-time coordinate, and then we apply the Feynman reparametrization to rewrite the dependence, then we obtain the following integral here. And lambda here is the integration of basically the Feynman as the here factor, the beta function. So I think what's particularly interesting is now when we combine those coordinates together, so this xa, which appear here, it's actually not, so we're taking basically a pair of coordinates which living in the RD, and if you know anything about embedding space, this corresponds to living on light point. But when we live on this, when we focus on this this particular combination arising naturally from the Feynman reparametrization, this actually belongs to, well, you can easily show even this is equal to -1. So instead, this is still living on an ADS, P plus 1 dimension of ADS space, living in our embedding space. And if I later on, or even some of you have been working on this subject a little bit, immediately recognize that if we interpret the lambda as my parameter, then basically this is nothing but describing a geodesic connecting, propagating inside the ADS, and with the endpoint being the two insertion point for the operator So using this knowledge, and we can actually do the following rewriting of the OP block which is given in terms of this final parameterization. And here the B012 is the unique tensor structure we have expressed earlier. So we are going to replace one of the D0 here is the polarization vector associated with the tensor primary field with the total operator for the contraction. So everything here will be integrated out. It only depends on the coordinate P1 and P2. And this is the starting point. We're going to try to find out the holographic interpretation of all this OP block. So, well, actually I mentioned that one of the reasons why this become the history is long, 40 years old, and it got resurfaced over the past few years was also because that this OP block become useful in computing the first order perturbation for the entanglement entropy. So basically you can express the first correction term in terms of those OP blocks. And they are other interesting story for the Platon Check and Yang Boa and also Monica Duica looking at this. But in all this paper, basically they focus on the scalar case, which is J equals 0, and the expression reduced to the following form. So I express this in a very kind of succinct way. Yeah, we basically define what's known as the HKL scalar field. And it's given in the following integral. The way we can think about it, this I should comment a little bit. So this was also done like in 2006, and in fact, they did it more for the more general cases. Tensor field, let's focus on simplest case that. The way they obtain, so this is basically an integral representation of a bulk scalar field propagating ADS space in terms of a boundary data. So in this case, we're looking at the boundary scalar field. And this is something like we teach our undergrad. So in the Poisson equation, now we give a source, and then we propagate with an integration measure. And this you might recognize is basically almost like the bulk boundary propagator. And in order to make this integral conformal, instead of taking the scaling dimension delta, it has to be taking this shadow scaling dimension. But the way they derive this rather simple formula is actually quite complicated, at least if you first look at the HKL paper. You really have to just solving the scalar Laplace equation in the ADS space and expand it in terms of the harmonic function, and eventually integrate over the kind of radial direction to actually reproduce this kernel, and this P0 corresponds to integrating over the remaining the boundary coordinate. So here we almost get it for free. I mean, basically from this OP block rewriting, literally, we can actually get this expression very easily. And this also leads to a kind of very natural interpretation of the OP block, which is nothing but we're basically taking this HKL field, and all we are doing is try to integrate this thing along the geodesic connecting the two external points, and with a particular integration measure, which correspond to differences in the scaling definition. So now for the general spin, this is something we did at the beginning of our forthcoming paper, is that we noticed that there's a nice identity to derive this tensor structure, and basically we can express this. This precisely only happens along the geodesic as a contraction between the geodesic itself and also the derivative, which is this antisymmetric tensor. And this actually allows us to rewrite the spinning case of an OP block into the following form. So I guess we could probably just focus on the very last line here. Now, here we have introduced the spinning generalization of this HKL field, and we have checked. Yeah, let me kind of unpack this expression a little bit. K here is basically the boundary propagator for the spin J tensor field. And again, you contract it with this boundary data of this tensor primary. And all it does is really change the polarization vector on the Z0 to this following combination. J here is the anti-symmetric, this is the rank 2 tensor. Hi.
Is it so that boundary to propagator, is it solution of the Franz-allocation then?
Is a solution to what?
Or Franz-allocation, because previous HKLF is the solution of the adjacent scalar.
Yeah, that's right.
But
So basically, this can be verified.
corresponding the spinning operator, so it might be related to this bulk scalar and bulk high speed field, and then.
Yeah, precisely. So actually, there's another way to derive the yeah. Okay, then we're going to show in a couple of slides. There's a way to derive the same expression from the 2-point function, and the 2-point function we know itself is going to be a solution, or the limit of the solution to the ADS equation of motion for the tensor field. So that way we can show this this expression is satisfied the equation of motion. Yeah, I'm going to show that. But the short answer to your question, yes. So, and I guess it's important here that we actually have this. So we are basically regarding this combination as a new polarization vector. And number one, yeah, even if you talk about whether this thing satisfies the boundary equation of motion or not, you want to preserve this. People know there's a gauge symmetry related to the polarization vector, of course, in the embedding space corresponds to this W by some copies of the ADS code. It's necessary to have this combination. So therefore, we have this very simple and clean picture for this, at least for the Euclidean case of the spin OP block. That's basically we're trying to, right, for the tensor field again, what we wrote down just now is nothing but a pullback of the tensor field along the geodesic, and you integrate along the geodesic connecting the P1 and P2. Indeed, there's another way. I mean, I haven't shown too much of detail to actually derive this the same expression for the HKLL cases. Now, it's actually considered this the following differential operator. And this is independent of all the polarization factor, and independent of whether you are living on a geodesic or this X here, this general bound point, ADS. Then you can consider the action of this differential operator on the both sides of this generic conformal integral. And in our case, X here is actually just a coordinate in ADS space, so this is -1. And what you see is that this is nothing but, of course, it's a scalar case of the boundary propagator. And what's inside, you have this copy of boundary and the boundary. So if you act on both sides, the reason why we introduce this differential operator is that there's identity relating the spinning case of the 2-point function in the CFT, and also the 2-point function, sorry, the boundary case for the spin J propagator with the scalar guy. So we can reach the following exactly the same relation, and it's dependent on what polarization vector or whatever point you are at. And to answer a question on the audience just now, that we also know the boundary propagator is basically nothing but a special limit, right? We generally know the propagator to satisfy so the green function, the ADS equation of motion for the tensor guy, take the limit along the point going to the boundary, but that does not affect we are only looking at derivatives, right? This the other remaining bound point X. This has to only to do with these remaining pieces. So this combination satisfies the equation of motion as well. So this is an easy way to see this works. And we also check that by projecting back to the physical space to satisfy all the other results in the HK. Well, of course, this is very closely also connected with on this picture, something I've been working on for about 4 years, and now Tsinghua University here, somewhere in Tsinghua University. So, yeah, so this is to do with this geodesic Venn diagram that Vijano proposed a few years back, and we, with a student from Kyoto and my student at NTU a couple of years ago, have generalized and extended the result frequently. But roughly speaking, that this is the holographic field for the conformal block, and that's what geodesic Venn diagram is computing. And this corresponds to basically, instead of computing a normal Venn diagram, where you restricted the two, so you select the channel, and like you do with ODE, and that basically allow you, tells you what kind of geodesics you're picking. And then the two boundary propagator, boundary propagator, two end of it, moving along those geodesics. But what we also realized that this boils down to a harmonic analysis in the ADS space, that we realize that actually the bound-to-bound propagator can actually be expressed in terms of a boundary integral involving the boundary propagator, where the scaling dimensions are related by the shadow density. So this is basically a building block, this kind of 3-point geodesic Venn diagram. So something we realize, and that allows you to actually verify case for arbitrary spin and other representations of that, and they basically bring everything on the shelf. Calculation is quite easy. Yeah, and from this picture, and compare with this picture, not surprising, right? Because one of the statements checked and other people were trying to say is that, yeah, the OP block, if you look at 2-point function, even though it's kind of ill-defined notion, so each of them are bilocal. Well, if you take two of them together, you're supposed to actually give you the conformal block of some overall coefficients. And this is almost trivially true that if you kind of just fuse two of them together and interpret it, we already kind of drag one field along geodesic connecting 1 and 2, and the other moving along geodesic 3 and 4 together precisely. Bound propagator restricted along geodesic, and all the other external guide corresponds to your scalar boundary propagator. This is precisely the correspondence that we generalize in D3 the spin J case. Good, so that was a good intro, and warm up for the Euclidean case, and for us to move into the real meat of the study the Lorentzian story of this game. So, okay, so roughly speaking, we can see where this goes. And so we have this very nice picture of dragging this, well, starting with, I guess, you're starting with this kind of shadow projection. So you can rewrite this in the 3-point function in some O along this. So basically, there's 3 issues that you have to deal with to generalize the Lorentzian. That's corresponding to all this question mark. So number 1, so now Euclidean, no need to deal with causality. So now for the Lorentzian, we really need to check different cases that P1 and P2, that they are conlike in space-like. And how that dictates the corresponding integration region. Previously it was doing blinding, integrating for the entire boundary. No need to worry. And in fact, for people in nodes, they also need to think about now what kind of 3-point function you should be using inside this integral. Weightman, what kind of continuation you should be doing. And finally, that from this, for each of those cases, you consistently define the generalization of this HALL field, and in fact, you will see that for different cases that this corresponds to different types of geodesics you should be considering. Azuma will basically explain those, answer those questions in more detail in his talk. But overall, this kind of belongs to a kind of more systematic program, which I guess I'm presume our students together right now. How to really think about, just basically, there are value and wisdoms in the context of Lorentzian version of the ADS CFT that hasn't really been explored in very much detail in the literature. Only in the past few years, I really start thinking about it. So previously, we just say, take Y where Euclidean, everything, tracing cross ratios, and they continue Y, but they are subtly rules. And then we comment a little bit on the next slide. So, so natural question, what's the Lorentzian generalization of HKL field, and how are their correlation function, map to corresponding diagrams, and so on. In order to answer those questions, number one, we noticed that for the Lorentzian CFT first, we are dealing with different kind of conformal symmetry group. Now, in general, it's SO D. The content is subgroup is different. For the quantum label is different. And so now, in addition to this delta order, which is fine, non-compact, and J belongs to the other SO1, which is also non-compact. And the really compact guy is the spin of this SOD-2 subgroup. So that means we should really view like this. J is also a continuous label, and then we can perform the same kind of shadow transformation on this label J, so as a spin shadow. I think that is boils down to the fact that the SO2, D while group is very different. It's not the previous case, we only have two-fold while group. Now we have this eightfold dihedral while group, which allow you to map to those for this different label. And the key point here is that all of them, right? I didn't write down the quadratic Kashmir equation. All this transformation leave the quadratic Kashmir equation in there, and so there's a eightfold degeneracy for given eigenvalue, but it's a totally different boundary condition. One for the main reason we care about those things more recently is that, of course, the famous work of Karen Pohl dealing with Lorentzian inversion formula. And we want to ask the question now, so now we actually involve all this, I just say, all this Heng-Yu non-local things that are given by integral transformation. What are they holographic? What's the orthogonality when we study the mathematical property? And they also have a nice connection with the integral system that is being explored in a lot of detail by Schomerus and collaborating with Daisy. So we want to basically do the ADS side of the story. And here, just to flash out that we have the individual, so the shadow transformation, now we're going from Euclidean to Lorentzian. We have an I here, not surprising, with rotation. But now for the spin shadow, we can also define similar kind of integral transformation involving those polarization vectors. And finally, there's a line rate transformation with spin operate along the line rate. This is related to the ANEC operating block. And you can always generalize the comparing polynomial. So one of the things we want to answer is, for example, what are those, how do we get a boundary propagator, vertices, and so on. Okay, that's my last slide. And but for our work related to OP log, so for example, now we do the shadow transformation with promote this spin shadow, promote the shadow transformation to full shadow. So we have to integrate both the boundary coordinate and the polarization vector. So for the spaceline case, well, when the two external boundary points on the spaceline, we have this very natural kind of proposal for the spinning Lorentzian block. Why it's almost the identical form with some different normalization constant consistency of repeating the use those transformations. The idea basically nothing but now you have to consider basically the shadow or the spin shadow transformation for the numerator spin and the shadow. this is our generalization for the HKL field. And from this, we can start computing, for example, about the boundary propagator. And this expression, I think, particularly allows us to directly map the non-local transformation of non-local operator and translate into the box and obtain these other ingredients we need to fully expose this oriented version radius here. Okay, so I pass the talk to Lu. Oh, hi, sorry, I shouldn't disappear yet.
Yeah, so,
Okay. Hi.
so HKL formula, this kernel, when you kernel you can define, but when you integrate over the space, there it's sometimes it's usually it's ill-defined, like a divergence. So in your case, how did you overcome that problem? Or probably slightly different.
Oh, I see. You mean like to actually perform the
integral,
do I worry about regularization? You mean like, for example, sorry, this expression.
Yeah, so probably left-hand side looks, I mean, finite. So there must be some difference from this original HKL formula. So what's the resolution?
Yeah. Okay. So. Yeah, we haven't thought about this issue about the actually performance. I mean, but this, yeah, this purely based on symmetry. But we haven't already much about with this. But I mean, later, I mean, good. So later in the Lorentzian case, in fact, in the Lorentzian case, then we will have a truncation of the integration region. But for the Euclidean case, yeah, we haven't really looked at this very good. Thanks.
Okay, any other questions? Okay, now let's thank Heng-Yu again. Next speaker is Tatsumani Shoka. He will continue with the same subject, part 2.